We already showed a proof of the Pythagorean theorem in the previous section, but there's another one that gets used all the time, and it's really actually very useful, especially for high school students. So we're going to assume that we have an arbitrary triangle, right triangle ABC, and without loss of generality, we're going to assume that the right angle is at A. And if it's not, we're just going to relabel our triangle so that the right angle is at A. Okay, so this is a really important connection. Anytime that I drop this altitude from the right angle to the hypotenuse, I split this right triangle up into three similar triangles. This is really important. So think about this, right? This triangle ADC is similar to the big triangle. Why? Well, they both have a right angle and they both include the angle C. So angle similarity, we only need two of the angles in two triangles to be the same. In Euclidean geometry, to know that they're similar, why? Well, because we know that the angle sum of a triangle is 180 degrees. So we know the third one has to be equal if two of the three are. So I know that I have right angle in both triangle ABC and triangle ADC. Wait, let's see. I have it here. Let me right? I know that triangle ADB is congruent to triangle CAB, right? ADB, so it goes short leg, right, is congruent to CAB, right? Short leg, long leg, right? I went short leg and then long leg, short leg, long leg. So that's right. And it is important to make sure that you label the triangles in the right order so that we have the actual correct triangles that are similar to each other. So CDA going short leg, long leg, and the same way CAB again, short leg, long leg. And they're both true by similarity, right? Angle for these, angle B is in both triangles. Another angle in the triangle is a right angle, so we know that we have it. And this is really all the setup. The rest is algebra. So what we're going to do is we're going to create proportions for C and B, right? So I'm going to create a proportion for C, a proportion for B, and let's show how that goes. Okay, so B over A. So notice that B is the hypotenuse of the small blue triangle, right? So I can put the hypotenuse B over the hypotenuse of the green triangle A. That's the first term. All right. But then looking at B, B is the short leg of the green triangle, right? So looking at B here, if it's the short leg of the green triangle, then it will be the way I can set up the proportion is it'll be proportional to W, which is the short leg of the small blue triangle. And notice that we went blue over green, right? So B is the hypotenuse in the blue, right? So B is the hypotenuse in the blue, A is the hypotenuse in the green. So we're going blue over green. So we go blue over green in both of these to set up this proportion here. And then I can clear out my denominators. When I multiply through by A and multiply through by B, I get B squared equals A times W. All right, and I do the same exact thing for C, and you can double check that I've done this correctly, that C is the hypotenuse of the larger blue triangle on the left, and A is the hypotenuse of the green triangle, and then C is the longer leg of the green triangle, and U is the longer leg of the left side larger blue triangle. And then we do the same thing, we clear out the denominators, and we see that C squared equals AU. And now we're almost done. Just a little bit of algebra and we're through this. The first thing to note is that this side A is equal to U plus W, right? So we can take W and add the line segment U to it, and they're going to add up to A. That's the key. And then all we do is we take equation 1 and add equation 2. When we take equation 1 and add equation 2, we get b squared plus c squared equals au plus aw. Then we're going to use this relation to substitute in. Well, first we factor out the a, then we can substitute in an a right here. So we have a times a, which is a squared. So there is the relationship a squared equals b squared plus c squared.